Einstein in his third paper of 1905 showed that there was a causality problem between Maxwell's electrodynamics and Galilean relativity, and that the only true issue was that Galilean relativity was unable to measure the speed of light, and therefore unable to see that as objects increase in velocity towards the speed of light, that a factor needs to be introduced to keep the speed of light constant. It was, however, Einstein's fourth paper of 1905 that brings us here today, and brings us into the theory of general relativity. After Einstein introduced special relativity by finding a problem between Maxwell and Galileo, he kind of repeats this process by attacking himself and his special principle of relativity, as there must be an effect on the principle of the conservation of energy, which might not be good. His fourth paper is very short, containing in the English translation only 717 words. As such, allow me to translate the English translation into something a little more digestible. The results of the previous investigation lead to a very interesting conclusion, which is here to be deduced. I based that investigation on the Maxwell-Hertz equations for empty space, together with the Maxwellian expressions for the electromagnetic energy of space, and, in addition, the principle of relativity. With these principles as my basis, I deduced the following results. Let there be a system of plane waves of light possessing the energy L in the system of coordinates S. If we introduce a new system of coordinates, S', moving in uniform parallel motion with respect to the system S, then, according to the system S', this quantity of light possesses the energy L times a relativistic shift. Let there be a stationary body in the system S, and let its energy, in the system S, be called E0. Let the energy of the body relative to the system S', moving as above with the velocity v, be called H0. Let this body, which remains at rest with respect to the system S, send out plane waves of light, of energy 1/2 L measured relatively to S in equal and opposite directions. The principle of energy conservation must apply to this process with respect to both systems of coordinates by the principle of relativity. If we call the energy of the body after the emission of light E1 or H1 respectively, measured relatively to the system S or S' respectively, then by employing the relation given above, we obtain that the energy of the stationary body at the start is equal to the energy of the stationary body after, plus 2 released packets of energy, which together have the energy L. Whereas from the S' moving frame, we measure that the original energy of the body, before sending out plane waves of light, is now equal to the energy of the body after, plus the energy of L with a relativistic adjustment. By subtraction, we obtain from these equations that the difference in the initial energies minus the final energies equals the original energy of the plane waves times gamma minus 1. The two differences of the form H minus E occurring in this expression have simple physical significations. H and E are energy values of the same body from two different systems of coordinates, which are in motion relative to each other, the body being at rest in one of the two systems, in system S. Thus it is clear that the difference h minus E can differ from the kinetic energy K of the body with respect to the other system S prime with the addition of a constant. The kinetic energy of the body with respect to S prime diminishes as a result of the emission of light, and the total decrease is independent of the properties of the body. Moreover, the difference K0 minus K1, the kinetic energy, depends on the velocity. From this equation, it directly follows that if a body gives off the energy L in the form of radiation, its mass diminishes by L over c squared. The fact that the energy withdrawn from the body becomes energy of radiation evidently makes no difference. So we are led to a more general conclusion that the mass of a body is a measure of its energy content, where L is a measure of energy. M equals E over c squared, or E equals mc squared. If the theory corresponds to the facts, radiation conveys inertia between the emitting and absorbing bodies. And with that final line, Einstein ties up all four of his 1905 papers. Having started by demonstrating Brownian motion is best explained by the existence of atoms, and then that light is a form of radiation energy which exists as quanta and can provide enough energy in a single hit when tuned properly in order to break the bonds between some metal, i.e. an atomic structure, and one of its electrons. He then proved that the motion of photons and electrons and other quantum particles are too fast for Galilean relativity to get accurate, and you need to account for that speed in terms of not just velocity, but of its components, length and time. And finally, that because of this fact of special relativity, it must also be the case that mass and energy are equivalent, and that in fact, the Brownian motion of paper 1 is caused by the fact that atoms exist as quantum particles who exchange energy through radiation, i.e. photons, and that photons are in fact a kind of massless mass-energy converter which conveys inertia between the emitting atoms and the absorbing atoms, thus moving them around. This also means that if you add energy to an object, say increase its temperature or force it near an object it is electrically repulsed from, then it will increase in mass. It also means, though, that if an object in motion perceives energy that is emitted from a body, it will perceive it with a relativistic shift. The kinetic energy of the object appears to be changed, and the laws of conservation of energy cannot allow for a loss or gain in energy without a counterbalance. Einstein thought about this for 2 years. Let us be Einstein ourselves and work this out. 1. Everywhere we go, the laws of physics are the same, even when we are in motion. 2. The speed of light is always constant. 3. Velocity is relative, and the faster our velocity, the bigger the difference in appearance of our length and time will be to others not moving along with us. 4. The faster our velocity, the bigger the apparent difference of kinetic energy, and therefore the bigger the apparent difference of mass to an observer who is not in our frame of reference. 5. Typically, when we think about mass, we think about heaviness and falling down. Given that falling is a form of motion and is related to mass, then falling is related to energy, which we also already know as that is the difference between potential and kinetic energy of massive objects. Therefore, there must be a relativistic effect here as well. 6. However, relativity has only really dealt with constant velocities, but we know from Galileo that all objects accelerate, that is, positively change velocities over time downward, and more so, that all objects accelerate down to the Earth at the same rate. 7. It thus can also be the case that the principle of relativity applies in some fashion to accelerated reference systems. Think about it like this. Again paraphrasing Einstein, what if a gravitational field is like an electric field, which is generated by a magneto-electric induction? What if the field only exists because of some relativistic effect? In such a field, where you are a charged particle and the electric field becomes more attractive the closer you get, you therefore accelerate towards it. What if gravity were as such? For example, if I placed you in empty space, meaning far from any other objects for millions of astronomical units, with a strong magnet in your pocket, then, somewhere in the distance, I place either a massive body or a super large magnet in the opposite polarity of yours. Before you know what the object is, you see me place something. And you see the moment that I do, that you slowly, at first, start moving towards me and the object. And over time, you start moving towards it faster and faster. Without seeing it, how would you know if you are falling towards a massive body through gravity or accelerating towards a magnet?
This video is possible thanks to contributions to the Existence University Patreon by viewers like you. Thank you.